Okay, guys, now this was not clear to people last time. So this you try section is where you don't do the problem with me, you do it yourself. You do this problem. So this problem here, you can try it by yourself if you don't want to take notes. So this is a side for notes. This is a side for you trying by yourself. And I recommend that you try it by yourself and then skip to the end of this and see if you got the same thing as me. I think that would behoove you. Okay, so at 3 p.m., I didn't use great English here because I was trying to write very little. At 3 p.m., oil tanker ruptures. Okay, that's our situation. Oil leaks at a rate of this liters per minute. How much oil leaks between 4 a.m. and 5 a.m.? All right, so this is a net change. Net change. So we'll go NTK for need to know. Net change theorem. Okay, and the net change theorem is in your part 1 packet, and it's this one, number 14. Okay, and this is the part 1 packet. So if you go all the way there, the net change theorem, the net change in F over a certain interval is given by the integral of its derivative. Okay, so that's what we need. Yeah, so really, guys, all that we need to do is say, and this is a rate. Okay, so this is already a derivative. Okay, so that's already a derivative because it says rate. Yeah, so we just go the integral. Okay, now here's the thing. I bet you for a multiple choice, they would put one of the choices as like, I don't know, what you'd get if you went 4 to 5 or something like that. So we have to think toward, okay, so it ruptured at 3 p.m. So at 3 p.m. is, and this is in minutes. At 3 p.m. is minute 0. At 4 p.m., darn it, I want these to be p.m. Yeah. Okay, at 4 p.m., it's minute 60. And at 5 p.m., it's minute 120. So that's how you have to be thinking. Okay, now this is a calculator section. This is a calculator section, so I just go here and I do math 9. Okay, so math 9. Math 9. 60 to 120. 100. Okay, and so actually, you know, guys, you know how I use approximation signs? They're not using them in the answers, and I just got a little bit paranoid that they would take off if we use them. I mean, I think that'd be ridiculous, but I'm just going to use equal signs, I guess. I don't think that they would, because that's true. It is these things are just approximations, but I'm going to use equal signs because in the book I have with like their answers, they're using equal signs, but okay, so there's that. This next one, I'm not even going to say anything. You can do this next one, or you could absolutely do that. Here's this one. This one was a little bit tricky. Number 3, so write this down. Suppose we've got this function g of x. I initially put a number there, but I didn't have whiteout, and I didn't want it. So write that down. We don't know this area. It is a negative area, though. And then this positive part has area 12. If the integral from 0 to 7 of g of x equals 9, and the integral from 0 to 7 of the absolute value of g of x equals 15, they want us to find this value right here, okay? Okay, so this, okay, so maybe I'll say let be, oh, we'll see. I'll say let equal, I don't know, b, I guess. Okay, so I'm going to let that equal b. So, so let's do this one first. Okay, so the integral from 0 to 7, and then g of x. Okay, so that's going to be this. Okay, so that's b. Okay, so this is 12 and this is b. Okay, so then this is going to equal negative b plus 12. Let's say that b is already positive. Okay, so let's let b be the positive area. But because it's under the x-axis, I'm going to be subtracting it. Okay, so negative b plus 12 equals 9. Okay, so now I've got to do this one. Okay, so from 0 to 7, and then the absolute value of g of x dx. And guys, this, to get an absolute value graph, you just reflect the negative parts over the x-axis, all right? So this here would get flipped up there if you were, because you have to negate all the negative parts. You have to reflect all the negative parts above the x-axis, so it would look like that. Okay, so and then this is going to be equal to b plus 12, and that's going to be 15. Yeah. So, oh, we didn't even need two equations, duh. And the one that you guys are going to do later, you do need it. Okay, anyway, this was still worth doing because you're going to have two equations because you'll have two variables, I think. So b is equal to 3. Yeah, okay. All right, so b equals 3. So you could have done this with just one piece of information. All right, now, this one. Okay, if g double prime of this function, if you're given that, how many points of inflection? All right, so this is, okay, so need to know Susan's table. Okay, so you would need to know Susan's table. And let me go to it. Alrighty, number 4. Okay, right here. So guys, I have the second derivative. Okay, so I have the second derivative, so I'm looking in this column here, okay? And I'm looking to see where the original graph has a point of inflection. Okay, so point of inflection on f corresponds to a sign change on f double prime. So I'm looking for a sign change. So I'm going to graph this. Okay, so okay, so I'm going to graph g double prime. All right, so this is sine of x squared plus 0.9. And I'm concerned with this interval here from 0 to 4. So I go to my window, 0 to 4 graph. Okay, now this is very, very important. A lot of people might say 0. they might say 0 here, that there are no sign changes because it doesn't look like it's ever going below the x-axis. But do not assume that. We've got to zero in. We've got to look closer at the parts where it looks like it just touches the x-axis. It might go down below more. So I'm going to go zoom. Oh, the very first one. Zoom box. This is like one of my favorite things that this does. It just gives you a lot of control over the size of your window. I'll go all the way to the end just in case it does something funny at the end. Okay, lo and behold. Okay, so the end looks pretty good. But actually, how many sign changes? 1, 2, 3, 4 sign changes. Okay. 4 sign changes on G double prime. So 4 points of inflection on G. And if you don't know that POI stands for point of inflection, then please write that down. Okay, number 5. You can absolutely do this. See your salmon packet, part 1, number 14. All right, you can absolutely do this. So write this down in case you get stuck. And now this one. Again, you can do this, but here are some facts to help. So please write this down. F has a jump discontinuity, and thank you, Lucas. Shout out to Lucas because you described it this way. And this is, in fact, the technical definition. So some facts to help. F has a jump discontinuity at x equals a if, first, the limit as x approaches a from the left exists, so equals some number. Maybe here we should say equals some number, because that's what that means. And the limit as x approaches a from the right exists, so same, equals some number, so not infinity. However, but the limit as x approaches a from the left is not equal to the limit as x approaches a from the right. Okay, so there is the definition, and I'm going to let you think it through from there. Okay, so this is what you're looking for when you're trying to figure out where the jump discontinuity is. And then number 7, you can absolutely do this. See Susan's table. Okay, I'll talk to you later.